Entropy, expected information from a process. So information surprisal is a logarithm. In particular, event A, the surprisal of A, is the negative log base 2 of the probability of A in units of bits. For a sample space S, probability distribution small p, I of x is the surprisal in the event, x is the outcome t of x. Defines a function I of x is equal to negative log base 2 of p of x. If all the outcomes are equally likely, then I of x can be calculated using shortest encodings of outcomes into binary strings. So for example, 8-sided fair die, we can say, well, is x bigger than 3? Then is x bigger than 1 or x bigger than 5? And then this series of decisions. And that gives us the possibility of our 8 outcomes for the 8-sided fair die. But notice each one of these outcomes can be encoded in strings of length 3 in binary. 2 encodes as 0, 1, 0. 7 encodes as 1, 1, 1. And the first level is the first digit equal to 1. And it looks like x greater than 1, x greater than 5 are two different questions, but actually both are just asking, is the second digit equal to 1? And these last 4 is the third digit equal to 1. There are 3 bits of information for each outcome of a fair 8-sided die. So information or surprisal is a logarithm. Suppose we have n trials of r possible outcomes. Surprisal is the fewest binary decisions that reveal all n trials as a percentage of n as n goes to infinity. For example, suppose r is equal to 2 to the h, and that each outcome is equally likely. Then we get this kind of a tree structure. And notice that this is the set of decisions, and we have to make h decisions to determine each of the r possible outcomes. So that means we have nh decisions, 1 for each trial, to identify all n trials. That's n log base 2 of r. And this is actually the fewest in this case. Surprisal is the h, the number of decisions. But that's the log base 2 of r, which is the negative log base 2 of 1 over r, which is the negative log base 2 of p. So let's look at a non-uniform example. Again, a spinner, but this time outcome 0 has probability of half and the other 2 have probability of fourth. That means the outcome 0 has 1 bit of information, whereas the other 2 outcomes have 2 bits of information. We can encode this information using this decision tree. If the first digit is 1, then we get 0 for no, and for yes we go on and look at the second digit, and for 2 we get 1, 0, and for 3 we get 1, 1. Notice outcome 0 occurs twice as often and is learned or identified via one single decision. Binary strings of length 1 for 1 decision, binary strings of length 2 when there's 2 decisions. So information means uncertainty transferred to knowledge. It can be encoded with an alphabet. We do this all the time. Words are comprised of letters of the alphabet. We include spaces and punctuation in that alphabet and instead talk about messages made out of characters. Hello world is a message with 12 characters. We can change to different alphabets. The simplest alphabet is 1, 0, the binary alphabet, and messages are often encoded as binary strings. Typically, the length of the message is greater than the amount of information it contains. You don't double what can be learned from a book by buying another copy of the book. That just increases redundancy, not information. So, alphabetic letters and symbols are represented by binary strings in the computer using Unicode. So the letter I is 1101001. N is 1101110. So the word independence as a binary string would look like this. This is the Unicode representation of the letters in the word independence. So the information in a message is determined by the length of its shortest binary representation in bits. For example, the standard Unicode binary string representation of the word independence can be zipped, in the same sense of a zip file, to be smaller than non-zipped. Here's the Unicode for the word independence, and here is its zipped representation. We haven't lost any information, but the zipped is 70 bits, taking advantage of the repetition of the EN and DE. And the amount of information, therefore, is no more than 70 bits, but there may be an even shorter encoding than zipping. So now let's look at the expected value of the self-information function on a sample space S with a given probability distribution, because it's the expected information from that probability distribution over S. So in particular, the expected value of self-information is called the Shannon entropy of the variable x, given by this formula. It's introduced by Claude Shannon in 1948 in a paper, A Mathematical Theory of Communication. For example, let's look at a spinner, this time with outcomes A, B, and C, and we'll just go ahead and use those labels. And the probability of A is a half, the probability of B and C is a fourth. The entropy, according to the formula, is given by this. Notice that the log base 2 of a half is -1, and the log base 2 of a fourth is -2. So we'll get a half times 1 plus a fourth times 2 plus a fourth times 2, and that's 3/2 bits. So in N trials that I guess the outcome for each trial, in half those trials I'll need one decision to learn the outcome, and in the other trials I'll need exactly 2 questions, as you can see by this binary tree. And the tree encodes binary strings. And notice that there's one string of length 1 and 2 of length 2. The average length is 3/2. Let's look at another example, again with a spinner. A, B, C, and D is the outcomes, but now with a half, a fourth, and C and D have probability of an eighth. This is the entropy, given by the formula. It's a half times 1 plus a fourth times 2 plus an eighth times 3 plus an eighth times 3, and that's 9/4, which is 1.75 bits. Now let's use what's called Huffman encoding. We look at our probabilities for our outcomes. We form a decision with the 2 smallest probabilities, in this case C and D, and then replace the 2 smallest probabilities with their sum. And then we just repeat. We do it again, and we do it again. We get a binary tree that encodes outcomes with these binary strings. And the average code length is 1.75. So if we have n trials of x, denoted x1 to xn, the outcomes of the n trials can be encoded as binary strings. The shortest strings possible corresponds to the fewest binary decisions. The entropy in bits is the average over n of the mean length of a shortest string and the limit as n goes to infinity. That is, the entropy of n trials of x is approximately n times h of x for large n and approaches exact as n goes to infinity. So suppose we have outcomes that are equally likely. The probability is 1 over r for r outcomes. So the self-information is just the negative log base 2 of 1 over r, but that's just the log base 2 of r. Shannon entropy is defined as you see here. Alternatively, Shannon entropy is just the expected surprisal or self-information. That's the sum of I of x times p of x. If there are equally likely outcomes, then we end up with the sum of log base 2 of r times p of x. The log base 2 of r doesn't involve any x's. The sum of the p of x's is 1, and therefore we get, if you have r equally likely outcomes, then the entropy is the log base 2 of r. Let's look at an example, a spinner with 3 equally likely outcomes, each with a probability of a third. The entropy is the log base 2 of 3, which is about 1.58496, so on and so forth. In one trial, we could form this kind of a tree, code length 1 and code length 2. That means we get 5/3 as the average for the 3. The average code length is 1.666 and repeating. But for 2 trials, we would have 9 possible outcomes. That would give us this kind of a tree. The average code length here is 1.6111, so on and so forth. In 3 trials, we'd have 27 outcomes, and when we form, again, this is actually using Huffman encoding, we end up with an average code length of 1.6. 4 trials, 81 outcomes, an average code length of 1.5895, and you can see as the number of trials goes to infinity, we're approaching that log base 2 of 3. Again, we're using here Huffman encoding. Now, if we have a probability of 0, then the surprisal is infinity, because the log base 2 of p of x, that would be negative infinity. So we instead need to use limits. The limit as p goes to 0 of p log base 2 of p is equal to 0. You can show that using calculus. So if p of x is equal to 0, when we set p of x log base 2 p of x equal to 0. Or we could say a better definition is Shannon entropy is a mean over non-zero probabilities. So let's look at more than one variable. So joint surprisal means that it's the surprisal from x being t sub x and y being u sub y in the same trial. Again, it's the negative log of a probability, in this case the joint probability. And we can define I of x to be the surprisal from x equals t sub x, and I of y to be the surprisal from y equals u sub y. And if x equals t of x, independent of y equals u sub y, then the joint probability is the product of the individual probabilities. And if we have independence, the self-information, surprisal, is equal to the sum of the surprisals. These are all functions on S, and even though I of x only has one variable, we can still think of it as a function of 2 variables. It just doesn't use the y. So that leads to the concept of joint entropy. So remember, this is our joint surprisal. Our joint entropy is the expected information from, or the expected joint surprisal, which is a double sum. It's the joint entropy of variables capital X and capital Y, the expected information from both X and Y. And notice that when we deal with pairs of outcomes, there are often pairs that have a probability of 0. So remember, we're actually only summing over non-zero probabilities. So let's look at an example of choosing cards. Jane chooses from 3 cards, numbers 0, 1, 2. John chooses a card from the 2 remaining. X is Jane's card, Y is John's card. This is the set of possible outcomes, each with a probability of a 1/6 of occurring. And we look at the joint entropy, but notice that 0, 0, 1, 1, and 2, 2 cannot happen because Jane and John can't have the same card. So therefore we have to be sure and sum over x not equal to y. Now the log base 2 of p of xy is the log base 2 of a 1/6. And we can pull it out front, get negative log base 2 of a 1/6 times this double sum, but that double sum adds up to 1, and we just get log base 2 of 6. So entropy is expected information. Self-information or surprisal is the amount of information that can be learned from the occurrence of an event, especially individual outcomes. I of x is negative log base 2 probability that x is x. Also surprisal, I of x is a function on the sample space. Entropy is the expected information from a variable x in that it's the expected value of that function I of x. And more generally, entropy is all the information expected from all the variables sampled by some process.